Welcome to Secure Software Development. We're going to begin this class the way we've begun every class so far by talking about banking software. Now, banking is a complex beast. There's lots of stuff to think about here. If we try to look at real banking source code, we'll be here all day and stuff won't fit on slides. If you're keen to look at real banking software, check out the notes in the slides. So as a result, we're going to use some very simplified pseudocode to try to get through this. But I think you'll see what's going on. Here's some code that does deduction, right? It's going to deduct some money from your account. You give it an account object and a transaction object, and we go ahead and we get the balance of the account. We put that in an integer value because it's very common to store these things in integers. This is for reasons I think we'll cover later on in the class. So we get the balance. We then check to see if the balance is less than the amount you want to deduct. If so, that's bad. You would be overdrawing your account. We don't allow that, so we fail the transaction and return false. Otherwise, we go ahead and we subtract the transaction value from your balance and set that as the new balance. We succeed the transaction and we return true. Okay? Failing a transaction, succeeding a transaction, this is something that shows up. It's basically where you're notifying the other party of the result of the transaction so they can keep track of what's going on. Great. That was pretty simple. And this is going to work. This is going to work most of the time in most circumstances because for your personal account, you're probably not using your card at some incredibly high rate of speed. You're not trying to withdraw from 3 ATMs at the same time. But just suppose that a scheduled transaction happens, there's an automatic deduction from your account for something, and maybe you're in a store doing something. A bunch of things happen at roughly the same time, and these different deductions are executed simultaneously in different threads. And let's think about what might happen. So here's one scenario. Over on the left, we have gotten a demand to deduct $2,000. Over on the right, we've got a demand to deduct $1,750. So we start out, we get your account balance, which is $3,250. We check to see if $3,250 is less than $2,000. It's not, so we don't fail the transaction. We go right on ahead, but context switch. A context switch happens, and now we're in the other thread. So we check your balance. Well, it's still $3,250. We then go ahead and check to see if $3,250 is less than $1,750. It's not, so we don't fail it. Instead, we go ahead and subtract $1,750 from $3,250, leaving you with $1,500 in your bank account. And we succeed the transaction. We notify the other party. They go ahead and update their books. We update ours, and then we return true. Now, we context switch back to the other thread, and we go ahead and do the balance update. Well, Bal over on this thread still holds $3,250, right? We don't know that the account balance has changed. Bal still has $3,250, so we go ahead and subtract $2,000 from $3,250, leaving you with $1,250 in your account, succeed the transaction, and we're done. So, on the one hand, that's good for you, I guess, because you have $1,250 in your account as opposed to being overdrawn by $500. But on the bad side, the bank is out $1,750, and they will figure it out at some point and come after you to get it. So what we have here is a condition where the order in which these things happen normally is fine. And if you had enough money, okay, maybe this might have still worked out, Or if the code had been a little bit different, it might have still worked out, maybe. So suppose one thing you might think is, well, instead of having that account, having BAL there, maybe I directly access the account stuff. Okay, maybe you do. The compiler is going to be smart. It's going to see that in this thread, account BAL is a non-volatile. It's going to go ahead and say, oh, I can put that in a register, and it's going to have exactly the same effect. So you need to mark BAL as volatile if you want that kind of thing to work. So it gets more complicated. Anyway, this is a problem. It's a problem called a race condition that I'm sure you're familiar with. There are data races. There's all kinds of different race conditions that come up when you're writing code. We sometimes call them hazards. And this is just a case where the correct functioning of the system depends on some relative timing that can be violated, right? You depend on sort of accidentally having the right timing. And you can, of course, accidentally not have the right timing and have one of these really hard to track down bugs where something weird happened, but you're not sure why. So with slightly different code, we might have the situation you see over here. And here I've drawn a little flowchart for you. Up at the top, in both threads, we check the balance is 3250. We have the pay demands. We check to see if you can honor them. In both cases, you can, right? These are running simultaneously. We then fulfill both of them. We fulfill the 2000. That sets your balance to 1250. On the other hand, we're past the checking. So we go ahead and pay the 1750, but we reference the balance correctly, and we set your balance to negative 500, which means we've overdrawn your account, even though the software is supposed to prevent that. And that's bad. Okay. So race conditions can show up, and they can have different effects depending upon how the system is written, and then the way in which the code gets interleaved. How do we fix it? Well, we fix it with the usual concurrency primitives. We can have semaphores or spin locks, other kinds of guards to block out and cause a portion of the code to be executed atomically. So over on the right now, we check the balance and it's 3250. Then there's a demand, and at this point we need to actually do some stuff with it. So we obtain a lock. We check to see if your balance is greater than 2000. It is. We fulfill the 2000 payment. We release the lock, and your balance is 1250. Over on the other side, we have a demand come in for 1750. We obtain the lock later. We have to wait for the lock to be released so we can obtain it. We then check to see if your balance is greater than 1750. It's not. Now it's 1250. So we fail that transaction and deny it, and things work the way we want them to. So that's what it looks like in the little flowcharts here. In code, it might look like what you see up here. So I've taken that do deduct pseudocode, and I've added some use of the pthreads mutex to it. So up at the top, I go ahead and I get a mutex, and I get a timed lock for that mutex. So if I can't get within a certain amount of time, I'll time out. We don't want the whole banking software to just block on your account. So we go ahead and we get that. We do the usual stuff, but you can see when we fail the transaction, we release the mutex. When we succeed the transaction, we release the mutex. So at those points, we can go ahead and another thread could proceed. Great. So every time we're accessing the balance, we're checking it, we're inside a chunk of code that is locked based on the balance. You have to have a mutex per account, and in this case, you can see the mutex is in fact part of the account structure. So there you go. You might be wondering, race conditions. Race conditions are something that everybody knows about. That wouldn't happen. So if you're curious about whether race conditions happen in like the Linux kernel, go and Google Linux vulnerability mutex and see some kernel vulnerabilities that were fixed by adding mutexes. All right. Code's not the only place where this stuff shows up. So let's consider this little circuit over on the left. This little circuit is kind of a sort of half of an SR latch. You could think of it as a pulse extender. So I've got my input D, and I've got a clock signal over there, and I've got an output Q. And the basic operation is that I set D, maybe I set it high, maybe I set it low. The clock transitions high, and that causes the value to be latched over on Q. And then the clock goes low, but the value we've locked into Q persists through that period. And it will persist until we make a change to D and we latch a new value. Okay? Now, that's the basic principle. But, I mean, there can be issues in circuits like this. So let's go ahead and see how it works correctly, and then we'll talk about what a problem might be. So bear with me, this is going to get a little complex. So over on the left, we see the circuit, and over on the right, we see a timing diagram. If you're not familiar with timing diagrams, they're not super complicated. We can see, for example, here that clock starts out 0, it rises to 1, and then over here it falls to 0, and it remains 0. And down here for Q, we can see that we don't know or don't care what the value of Q is in this little gray section. But then we know that it's 1 here and persists as 1 later on. So that's how you'd read that. And I've broken them up. I've indicated which signals correspond to the inputs to each gate. So clock and D are the inputs to AND 1. The inverted clock and the prior Q signal, or the output of the OR, are the input to AND 2. And AND 1 and AND 2 are the inputs to the OR. So there you go. So let's see what happens. We'll suppose that we set D to 1. So we see here after that D rises to 1. The clock subsequently rises to 1. And then after a small delay within the gate, we see that AND 1, down here at the bottom, also rises to 1. So inputs D and clock are both 1, and so AND 1 then generates 1 as an output, which it feeds into the OR. So after a small delay again, propagation delay, OR rises to 1. So now the output of OR is 1. We don't actually have to know what's coming out of AND 2 or care. If either one of the inputs to the OR is high, is 1, then the output of the OR will be 1, and we'll just go on. So that's in fact what happens, and so we set the output of the OR to 1, which means Q to the output of the OR is set to 1 right here. Great. So there we go. In addition, we'll notice a few other little things. The clock signal passes through an inverter and passes into AND 2, so we have the inverted clock. That's what this little clock with the bar over it is. And so you can see that the clock goes to 1 up here, and after a small propagation delay, the inverted clock falls to 0. So the inverted clock is 0. And we also see that Q, or the output of OR, is passed back into AND 2. So the two signals in the middle, the inverted clock and Q, are the inputs to AND 2, which you can see here we now know after this point is 0. There you go. Pretty simple stuff. What happens when the clock falls? So over here on the more extreme right, we see the clock falling back to 0. When the clock falls to 0, we have at least one of the inputs to AND 1 now 0, which means that AND 1, after, again, some propagation delay, will fall to 0. That means one of the inputs to the OR is now 0. Maybe both are now 0. But if we take a look at this, we'll see that the inverted clock, after a small delay to go through the inverter, rises to 1 at about the same time as AND produces its result. So now we have a 1 here. The prior value of Q was still 1, So both the inputs to AND 2 are 1, which means that Q remains 1. So we can see that even when the clock falls and this AND basically turns off, let's say, it results in the other AND being turned on, and the whole thing then persists the value of 1. That's how it's intended to work. But, let's suppose the inverter is a little slower. Now, why would it be slower? Well, it could be slower because of path length issues. It could be slower because there's a defect in the materials that are there. It could be environmental effects. A number of things can cause a delay within a part of a circuit. Okay, and we'll assume a small delay. So you see, you can sort of maybe see these little hashed marks here that, 1 time step, 2 time steps. We'll delay the inverted clock by 1 additional time step. So the clock falls to 0 here. We don't care about D after this point. So the clock falls to 0 here, and normally we would expect after a small delay, the inverted clock would rise. But let's delay it 1 more time step so it rises here. So as a result, the clock doesn't rise for a little bit. So when this falls to 0, that sets the output of AND 1 to 0, and we see after a small propagation delay, AND 1 goes to 0. Now, at this point, AND 1 is 0, AND 2 is 0, so both inputs to the OR are 0, so after a propagation delay, OR falls to 0, at about the same time the inverted clock finally arrives, but it arrives too late. It gets there too late, too bad, OR has already dropped to 0, which means Q has dropped to 0, and our little circuit is broken. It's not persisting the value on the output. All right. So your race conditions can show up in software, they can show up in hardware, and hardware logic race conditions there's a CWE for that as well, right? There's CWEs for both software and for hardware. Great. So let's switch gears and let's talk about creating processes. We're building to something, so stay with me. So if you're making a new process in Linux, how do you do that? Well, does the kernel go in and set up all these structures in memory and propagate them and build all this stuff? No, that would take too long. It does basically what you would think. It says, I don't want to do all this work. I'm going to copy somebody else's work. And that's what it does. Fork basically copies an already existing process and just makes a duplicate of it. It's the easiest way to get a new process. Just duplicate a process that you already made. And that's how they all work. There's some code over on the right that will let you play with fork. If you've never done anything with it, surely you have. But if you haven't, you can monkey around with it over there and look at the process IDs, etc. as they come back. Every process, with the exception of init, is started by copying another process with fork. And that can include things like upstart and systemd. On some systems, you may wonder, well, what is init? And you may poke around and you may find that it's like a symlink, or appears to be a symlink to systemd, but that's a whole thing we don't want to get into. Basically, the kernel has an init option that will specify what it wants to start. If you don't specify it, it has a list of things to try, eventually dropping down to like bin sh if it can't get anything else to run. All right, so init actually has to be created, but after that, we do all of the process creation by just duplicating an existing process. That seems simple, right? You just duplicate an existing process. Well, there's a little more to it than that. The fork function is actually a system call. So I don't want to get into what system calls are, but just think of them as a way for me to reach into the kernel and call something within the kernel, causing a context switch and letting the kernel run. So I call into the kernel to do some work for me, in this case, to build a function. Fork doesn't take any arguments, and it does all the things you see there, and actually a few more things There's a link at the bottom if you want more gory details about what it does. But the main thing it does is it duplicates the calling process's memory. It duplicates its page table, file descriptors, directory streams, etc., etc. The child process gets a process ID, and its parent process ID is set to the caller. And then various things are reset to 0. The execution time is obviously set to 0. Alarms are canceled and timers are set to 0. File locks and signals pending are cleared. That makes sense. You don't want the child to inherit the same locks as the parent, because then how would you coordinate unlocking the file? And then the child is scheduled to run using the same return address as the parent. That's right, the child and the parent look exactly the same, and the child will start running right after the fork call, the same as the parent. Well, how do I know which one's which, right? How do I know whether I'm the parent or the child? And the way I know that is that I look at the return value of fork, and I have 3 possibilities. It comes back as a negative value. Oh, okay, fork failed. Something went wrong. Maybe I couldn't get memory. Maybe I hit one of the system limits. Okay, so those are bad things. And so maybe it just terminated based on that. Maybe I accidentally coded a fork bomb. If you're not familiar with a fork bomb, look it up. And I hit a limit, right? There are system limits to prevent the fork bomb from taking down my system. So I hit a system limit and it began to kill my processes. If I get back a 0, I'm the child. If I say, what's the result of this fork? And it's 0, that means I'm the child. If I get back a positive, non-zero value, that result is actually my child's PID, and I'm the parent. There you go. Once again, Linux has solved a complex philosophical challenge. I make a duplicate of the ship of Theseus. Which one's the real ship? Well, that's easy. It's the one that gets the child's PID. Done. Easy. Take that, philosophers. We usually don't want a copy of the parent process, right? It's not often the case that we're doing this because we just want a duplicate of the parent process. We want to start a different process. We still fork to create the bones of the process, but then we use the exec system calls, right? Exec v, exec ve. They all sort of eventually trickle down to exec ve. And what those do is they take an image, right? Typically we point to some file on disk, and it overwrites our process with the image off disk. Once it's done that, it sets the entry point, the return value, right? When the kernel's done and it returns to user space, it will load the program counter with some address. For fork, it just loads it with the same one as the parent. But in this case, that doesn't make sense. That would just be pointing somewhere into some random stuff. So instead what it does is it finds the entry point for the image you load, and it sets the instruction pointer to the entry point, and so your program begins running at the beginning like you would want it to. So here's what happens. You call fork to make a new process. You call exec to then load an executable into that process space and start it running. Pretty simple. Now, the problem with this is it's wasteful. We spent all this time copying our parent process, duplicating it laboriously, and then we just throw it away and override it. Well, that seems bad. Right? We don't want to do that. So we don't. Instead, what we do, right? How do we make a new process? We cheated. We copied off somebody else. How do we start one? We cheat. We use virtual memory. Remember, all memory is, in fact, virtual. So, right, when we start out, we want to make a copy of the parent's address space. And in a sense, we do. But what we basically do is we give the child the same page table as the parent, but we make the pages read-only. Now, what does this mean? Well, look over on the right-hand side there. We've made the page read-only. We know the page should be read-write, but for right now, it's marked read-only. We actually mark it specially, so we know that, but don't worry about that right now. It's read-only. We also keep a reference count of the different processes that reference each page. Why do we do that? Well, we might fork. We might do a whole bunch of them, in which case we wind up with several different processes pointing to a page, and we want to keep track of how many different processes are pointing to that page. So we keep a reference count. In this case, we see P1 and P2 are pointing to page X, which is read-only, so our reference count is 2. Now, what happens when a process wants to write to that page? Well, one of two things is going to happen. If the page was originally read-only, like it was maybe part of executable, and we try to keep executable pages read-only. We don't want them to be writable. So then we'll just fail. But it might be that the page was originally a writable page, in which case we would like to allow that write, but we don't want to overwrite the page that everyone's pointing to. So we get a fault from the memory system because it's a read-only page, but we know that page should be read-write. So what we do is at that point we copy the page. We make a duplicate of it somewhere else in physical memory. We update the child's page table so it's got the same address as it always had, but now it points to a different place in physical memory. Remember, all memory is virtual, so I just point that to a different place in physical memory, and I mark the page as writable, and I complete the write. So what I did was I copied the page when the child tried to write to it. If the child never tried to write to it, I wouldn't bother to copy it. It saves me a huge amount of time, right? If I make a copy of the entire process with fork, I'm not going to use most of those pages, especially if I immediately exec. So that saves me from having to make any copies, right? This becomes a bookkeeping exercise. So we call this copy on write, abbreviated or initialized COW, or cow. And copy on write is a really super useful technique, not just for fork and exec, but for a lot of things. There are some security tricks you can do. I can keep a page initialized to 0, and then I just do a copy on write whenever I allocate a new page so that memory is always erased. So I grab a page and it comes back to me full of zeros. And I can't grab a page and then paw through it looking for previous page owner's secrets because the page got zeroed out. It speeds things up. If I had to allocate all these pages and then I had to deallocate all these pages, that would be terrible. So I don't do all that stuff, right? I save a lot of time by using copy on write because maybe I never have to copy. Virtualization. The kernel can use same page merging, which allows sharing the same page among multiple virtual machines. And when virtual machine X wants to write to that page, at that point we make a copy. So we can dramatically reduce the memory pressure of running many virtual machines by using copy on write. If we could find duplicate pages, we can deduplicate, we can merge them, and that would be a potential savings in memory. It's a little harder, it takes a lot of work, but you could do it. C++98 actually had copy on write strings. Those got eliminated in C++11, and there's a story there. But, again, pretty good idea. Snapshots. The ZFS file system uses copy on write to reduce overhead, and that's just the initial list that I got tired of typing, and so plenty more uses of this technique. It's so useful, we should use it everywhere, all the time, for everything, right? Because what could go wrong? It's a good technique. What could go wrong is CVE 2016-5195, where we discover it's possible to exploit a race condition. Remember those? Remember race conditions? Bet you thought I forgot about race conditions. It's possible to exploit a race condition to allow unprivileged processes to overwrite read-only memory. And that's bad. That turns out to be a bad thing. Okay, let's see how that works. So I'm going to give you a little graphic demo that comes off of the internet. I think it's really good. I've rewritten a little bit of the text from it. You can go see the original at that link. If you're like me and you want to see like actual code that you can compile and mess around with, that second link will take you to actual code that pretty closely follows the DotyCow demo. If you want other code to do this, it's in the slide notes, and you'll find a link to a whole bunch of proof of concepts of DotyCow. You'll need to, if you want to actually do this, you'll need to go and get a version of Linux prior to this being patched, maybe build a virtual machine, and then you can run this and have lots of fun with it. So here's our initial situation. We have our process, DotyCow.c, over there on the left-hand side. In the middle, we have the kernel, and we have our process's virtual address space. Why is that over there with the kernel? Because the kernel actually lives in our process's virtual address space. The kernel and its memory are mapped into our virtual address space. And then over on the far right, we have physical memory. Okay? Remember, virtual is an address space. Everything is ultimately in physical memory somewhere, but I can point any part of virtual space to any part of physical space. All right, so you got all that in your head. Life is good. Over there, we see a root file. That's some file that we could read, but we can't write. Are there files like that? Sure. Password is a file like that. The sudo file is a file like that. Any certificate is a file like that, right? When you connect to a website, you're going to verify a certificate back through your certificate chain. Your process running as your user has to be able to read those certificates, but it shouldn't be able to write them. If it could write those certificates, it could cause mischief, so we don't want that. So there we go. So our little process, DotyCow, is over here. The file we can read but not write is over there in physical memory, and we're good. So here's what we do. We go ahead and we ask the kernel, and we use a system call called mmap to create a private mapping of the root file in our virtual memory. And that's okay. We can do that, right? We can say, go ahead and read that file into my virtual address space, or give me a mapping to that file in my virtual address space. And once we have a copy of it, we can modify the copy. It's fine for us to get a writable copy of it. It's just not okay for us to write to the original, right? Keep that in mind, okay? So we say, hey, kernel, I would like a copy of root file to be mapped into my virtual address space. And the kernel says, okay, I can do that. In order for me to do that, I need to go ahead and create a spot for that. Okay? It needs to find a spot in physical memory to store our private mapping. But wait. Copy on write. The kernel doesn't have to actually go and allocate more physical memory. It can give us a copy on write copy of the root file. So instead of doing all that work, it says, okay, I'm not going to do that. I'm going to go ahead and give you a copy on write version of the root file. And it does it. It gives us a private mapping in our virtual address space. So now that private mapping, this virtual, it's not memory, it's virtual memory. This all points to the actual real root file over there. But if we try to write to our address space, it will do a copy on write so that our changes will not overwrite the actual root file that is read-only. All right, so far so good? Okay. So now we have our own little private copy. mmap has finished its work, and now we decide to do some stuff. We want to write into that file. But if we just straight up write into our memory, we're going to trigger the copy on write. We're going to trigger a processor exception, which is going to cause a copy on write, and we won't get to do the bad stuff we're trying to do. So instead, what we do is we reach out indirectly to our own memory. How do we do that? How do we reach out indirectly? There's a couple different ways to do it. The most common, and the one that's in the example, the source example that I gave you, is to reach out through the proc file system. So I don't know if you know what the proc file system is. If you don't, you can read about it at the link in Note 1. But basically, the proc file system is a virtual file system. It's not really files on your disk. It looks like files on your disk, but it's really a virtual system that provides you with information about the running Linux system. You can look in there and you'll find information about the processor, about hardware, and you'll find information about all of the processes. All processes in there have a little directory for that's named after the process ID. And within there, you can find stuff like your memory map for your process. And if your process looks in proc self, it'll find its own memory mapping in proc self mem, and it can go look at it, right? Everybody who looks at proc self will see their own memory mapping. So proc self mem contains a representation of dirtycow.c's virtual memory. Okay, now what we're going to do is, instead of writing directly into our memory, we're going to write indirectly through proc self mem, because that gets the kernel involved, and the kernel has to use its process-to-process systems in order to do the write for us, to mediate that write for us. Now, as an aside, this technique doesn't work everywhere. You have to use different ones on some platforms. On, I think it's Red Hat, you're not allowed to write to proc self mem, which causes this technique to break. But you can use other techniques to get there. You could use ptrace and some other stuff. All right, so we're writing to our private space, but we're doing it indirectly through the kernel. So we ask the kernel to write moo out into our private mapping for us instead of doing that. And the kernel's like, yeah, fine, I'll do that for you. Okay, so now the kernel has this challenge. It's like, where do I write this? Okay, I've got this private mapping here, which points to this physical memory. Do I write it out to the physical memory, or do I have to allocate some new stuff to write it out? Where is it going to be written? So the kernel probes the original root file, right? It tries to write to it, but it gets an exception. And that means it's now got to create a private copy for us. That's the copy on write. So it tries to write, but get an exception. It says, oh, I've got to allocate memory, and I have to then, I can write to the copy of the memory, which isn't what we want. So we interrupt this process, okay? This is what it's going to do. It's going to go ahead and create some memory for us, but we're going to jump in the middle of that and cause a race condition, hopefully to get around that. So it's creating a private mapping, a copy on write mapping, and we'll update our page table to point to that new private mapping. But before all that gets done, we go ahead and tell the kernel, oh, you know what? I don't need that private mapping anymore. The way we do that is through another system call, which is madvise. And so we invoke madvise, we give it don't need, so it knows we don't need that anymore. And it's like, oh, okay, you don't need that anymore, so I will forget the private mapping. No problem, done. So then the kernel goes back to what it was doing before, which was writing out moo, in this case, for us. It's writing out something for us. And so it writes out to the only place it has to write it out, which is the original file. The write continues, and we're done. We've now succeeded in overwriting the read-only file. The kernel has done that for us. Thank you, kernel. And you notice it wrote it directly into the read-only copy. There you have it. That's how it works. It's a combination of a number of techniques, like most really devious vulnerabilities are. So what was that file? It could have been the password file, the sudo file, certificates. Could have been anything. And we got to override it because of this. We have to get the timing just right to break in. And if you look at the source code for it, you'll see that it involves trying a whole bunch of times really fast. And you might not always get it. So you might have to try it 2 or 3 times before you get succeed. This is a good instance, a good place to indicate why security is different from reliability. So suppose there's a 1 in a billion chance of this working. Great. I can discard that from a reliability point of view because maybe I just don't care. That's too small, right? A random happenstance, not going to happen. But if from a security perspective, I'm just going to run it a billion times. I'll run it 10 billion times because computers are fast and I really want in. And so I'll run it a ton of times, and one of those will succeed statistically, and I'll get in. All right. It turns out, this is a quote from Linus Torvalds. It comes from a commit message, and all the commits in this are hyperlinks, and you can go look at the commits, and you can go look at the message directly. So Linus Torvalds says, hey, this was an ancient bug that I tried to fix, but then the fix got broken by another fix, and so this time let's actually fix it. And so they come up with a fix and submit that, and that's in that last commit there. Do you want to see the code that leads to these issues? You can go and look at those commits and see them. So, 2007, or 18TS, that's the year that Dirty Cow, that vulnerability, first appears in Linux. 2007. 9 years later, in 2016, people notice it. It's on the list of exploited vulnerabilities, so who knows how long people were exploiting it. But it was discovered and publicly disclosed in 2016. There's the CVE for it. You can go look at that. And there's a link to a whole bunch of proof of concept. There's a whole GitHub repository of proof of concept code if you want to paw through to that. It gets a 7. That's not the highest score, right? That's not an Olympic level score for vulnerabilities. That gets it, probably wouldn't even get it a silver medal. You have to be on the machine to do this, so you've already maybe gotten in. This is a way to modify a read-only file, and you can probably use that to engineer your way to privilege escalation. So you're on the machine. This is a way to do privilege escalation, but it requires certain things to be true. Now, why go through this? This was from 2016. Geez, Stacy, that's an old one. Well, it's being used. It's still being used. So the point is to illustrate something about vulnerabilities. So over on the right, we see a snippet from Akamai's paper on a new Magneto campaign, people who are attacking point-of-sale terminals. And we find that one of the things that they're using to do this is Dirty Cow. So there you go, being used in August of 2023, which is when this report came out, probably still being used because it's not that much after that. 2016 to 2023, another 7 years of this thing, right? What's happening here? Well, Dark Reading has a really good little paper on this that you can go read. And here's a quote from that. Nearly 60% of organizations that suffered a data breach in the past 2 years cite a known vulnerability for which they've not yet patched. 60%! It's a known vulnerability. So, What about 0 days? 0 days are the scary ones, right? They're the ones that no one knows about. They're going to get you in there. Flexera looked at this and they found that only 14 of the 20,000 known software flaws were 0 days. Not 14,000, not 1,400, 14 out of 20,000. And that's a decrease, right? You don't need 0 days when the other stuff will work. And it's probably easier because there are GitHub repositories of proof of concept code you can go and read. So you can go and read how the exploit works and then try it out because people haven't patched these systems. All right. So what are the takeaways from this? We're going to develop software. What does this mean to us? Well, we already know the first thing here, right? All systems are vulnerable. Maybe they're vulnerable because we made a mistake. Maybe they're vulnerable because there is a miscommunication between two systems, or there is some standard that we assume is going to hold, but no one's really enforcing it. Or maybe there's a vulnerability because the most recent, highest patch level, just downloaded it fresh off the internet, good to go, version of a library contains a known and exploited vulnerability. Could that happen? It could absolutely happen. And of course, race conditions tell us to do things like try to check all the execution paths and see if we can reach an insecure state. That's the domain of things like model checkers and so forth. We'll cover that in just a moment. All systems are vulnerable, so you should use tools to help you out. This is going to be a very tool-heavy series of slides. Software composition analysis tools check for known vulnerabilities in component libraries of your project. And I've linked to a Medium post and to a GitHub page for lists of these. They're not comprehensive. The one that I use for Rust is Rust Audit, which is not either one of these lists. So there are plenty of them out there. Go find the one that's relevant to the kind of software you're developing. Execution paths, I mentioned that. Consider a static analysis security testing tool, a SAST tool. And again, I give you a Medium post and a GitHub page. And I even point out a place where you can go and look for race conditions. Thread Sanitizer is part of the LLVM compiler suite, and you can go and take a look at that at the link. Finally, source code security analyzers are awesome. If you can go and find one that is relevant to what you're doing, that's great. Don't just grab them all and run them all, right? They're going to produce a ton of false positives. They're going to give you irrelevant information. You need to go and find the ones that are relevant to what you're doing, that make sense in your environment, and understand them so you can separate good alerts from bad alerts, so that you can configure them so that you get fewer bad alerts, right? There's stuff you've got to do to make them work. Great. Let's talk about the Graham-Denning model. That's another security model. So we've talked about a couple of security models. We're going to talk about a couple more, and then we'll be done. Computer systems are dynamic systems, and things change, right? Remember the tranquility principle? We said, well, what happens if we change the confidentiality or the integrity of either the subjects or the objects at runtime? Well, that's confusing. Don't do it. Okay, well, that's not practical, right? We have to take into account what happens when things change. And so a useful security model is going to have to account for dynamic changes that occur during system execution. The Graham-Denning model begins to do this. It was developed in 1972 by Scott Graham and Peter Denning. And again, it's going to use this familiar language that we've been using for the other models. They're going to be subjects, and the subjects could be users, they could be processes, they could be other systems. There's something that's going to interact with the system to do information processing. And there are objects, right? The objects are the files or the directories, right? They're the objects that are manipulated by the system. The Graham-Denning model also adds an explicit set of writes. So previous models have said, yeah, there's write and there's read and there's read-write. Graham-Denning says there are writes. And I don't know what they are, but there are writes. And so you've got a set of writes. And you can think of them as tokens if you want. And I have an access control matrix, and I treat that as a first-class object. So in the past, we've said, well, there's this hypothetical access control matrix. It's still hypothetical. Graham-Denning doesn't require that you write the whole thing down and implement it in code. It basically uses it and tells you how the access control matrix changes, how you store the results of that, how you implement it is up to you. So you can see over on the right-hand side, S is our set of subjects, O is our set of objects, R is our set of writes, and the access control matrix is A. One important change is that the access control matrix specifies the rights of subjects, right? Think of the rows, one row per subject. It specifies those rights on both objects and on other subjects. So you'll see this little funny thing down here on the right for all subjects and for all O, where O could be a subject or an object. We define the access to be some subset of the rights. Could be empty, no rights. Could be all of R, all the rights. Could be some other subset. Okay? But we're able to specify one subject's rights with respect to another subject or with respect to an object. The model defines 8 primitive protection rights. So this is where it begins to define what it means by protection rights. And 4 of them are over on the side here. And I think they're pretty obvious. Create and delete object, create and delete subject. And you can read the description, right? Create and delete object allow the commanding subject, the person who's running this command, to add or remove an object. Okay? These primitive protection rights are meant to be commands to the system. Okay? So there are 4. We got 4 more to go. Let's go and add 3 more. So for each object, one subject is going to be the owner. Should make sense, right? You look at a file in a Unix file system or a Linux file system, and it's got one owner. It has an owner specified for that file. Same thing here, right? Each object has one subject that is that object's owner. But in addition, for each subject, we can designate another subject as the controller for that subject, right? So maybe if I hire you, I become your controller. So we have a notion of an owner, of an object, and a controller of a subject. That's great language. Nothing seems wrong with that to me at all. The access control matrix also holds the owner and controller designations. So if I make myself the controller for Alice, I go and look in the access control matrix, and I find my row, and I find Alice's column, and I put control in that cell to indicate that I am the controller for Alice. Now, an important distinction to make is a distinction between protection rights and access rights. An access right is my ability to read a file, to write to a file, to delete a file, to print a file, to execute a file. Those kinds of things are access rights. Reading an access right, granting access rights, deleting access rights, adding subjects, deleting subjects, those are protection rights. Okay? We know that access rights are stored in the access control matrix. Who has these other rights? Well, we can set that up however we want it, right? The model doesn't specify all that for us. But remember, keep them separate. Protection rights and access rights. within the Graham-Denning model, some rights can be marked as transferable. So I could have the right to read a file, or I could have the right to read a file and it's also a transferable right. And that gives me this protection right over here, which is transfer access. This allows the person executing the command to transfer one of its rights to another subject, provided that right is in fact transferable. Now, transfer sounds like I take it away from me and add it to you, but that's not what it means here. What it means is I have it and I grant it to you as well, and now you have that right. So, but I can only do that if I have a copy of the right that is transferable. So I have to have a special version of it that's transferable, and then that allows me to transfer it to you. If I have the right to read a file, but that right is not transferable, I can't transfer it. So here's a summary of how all this works. This table is important. You should be aware of where this table is in the lecture slides, because you're going to come back to it for the homework. So you see the commands over on the left-hand column. You see a precondition in the middle, and you see the effect over on the right-hand side. So if I want to delete the access right R of subject S on object O, I have to be sure that I'm the controller for subject S, or that I am the owner of object O. Either one of those will let me remove the right R from that entry in the control matrix. Okay? At the bottom, the last row, you see the use of an asterisk there. The asterisk indicates that the right is transferable. So I say I want to transfer a right. Let's say I want to give you permission to read a file. I have to have a transferable copy in my entry of the access control matrix. So I look for R star in AX0. So X is me, O is the object, AXO. If I find it, then I can transfer either R or R star. I can add either one of those to your entry in the matrix for that object. So I have a transferable right, and I can give you just the right, or I can give you a transferable version of the right that you could transfer onto someone else. Hope that makes sense. The Graham-Denning model gives us the properties that will allow us to model most access control systems. Okay? And that's great. This gets us really far down the road. This is already a much more useful model. But think what we've given away. In the Bell-LaPadula model, we had a simple model with strict controls, centrally managed, and it was set up so that we couldn't leak information. And that was great. What about this model? We haven't said anything about whether we leak information, right? We would have to do some kind of complicated proof about structures in this model to figure out if information is leaked. And that might be really hard, because this model, this model has a lot of moving pieces, and some of them are fairly complex. So what do we even mean by that? How would we know if we were leaking data? Well, we might leak data if we leak permissions. So suppose I start out with some access control matrix. And of course, over time, that matrix is going to evolve. I'm going to add rows and columns, maybe delete rows and columns. I'm going to add rights to different places in that, different cells in there. And some of them will be transferable and some of them won't be. What happens if I reach a state where, oops, I've given the wrong person a right? The worst case would be that I, as the owner of an object, outside my control, without my knowledge, have somebody else gain access to that object. And that can happen, right? So I transfer a right to let's say Alice, and she transfers that right to Bob. And then Bob, I didn't even know Bob had that right. Bob reaches out and modifies an object I own. Wait, I didn't think that was possible. I own this object, and I only gave rights to Alice. I didn't know that Alice had done this as well. Okay, so you can see the problems that may occur. How could I deal with that? Well, that was the challenge that was met by the HRU Security Model. So they wanted to answer the question, will a subject ever have access to a given object? And so Michael Harrison, Walter Russo, and Jeffrey Ullman, that's the HRU, wanted to explore whether a protection system was safe and whether they could prove it for a given system. So here there's a lot of things we have to define. We have to define safety. We have to define what a protection system is. You may have some books where Russo or Ullman contributed. If you do, they're probably fairly technical books. When I was doing my degree, I used the Hopcroft and Ullman book on finite automata and pushdown automata and Turing machines and computing theory and complexity theory. And it's very technical, right? So you can imagine they're going to come to this problem with that same degree of, let's pin everything down and let's actually explore the space using the discrete math of computing. And that's what they do. HRU model is a fairly simple but very formal model. All right, so what is safety? So under this, safety is defined to be the ability to decide who can obtain certain rights to objects by a sequence of command invocations. Okay, so if I can control that, then presumably it's up to me and I can keep the system safe. The HRU model formalizes these ideas, and it does that by building on the Graham-Denning model. So remember, the Graham-Denning model had subjects, objects, rights, and an access control matrix. HRU is going to start there and then build on it. So you remember Graham-Denning had these 8 primitive rights. Well, HRU defines 6 primitive operations. Create an object, create and destroy an object or a subject, enter a particular right into the access matrix, or delete a right from the access matrix. And that's all you need. So remember, for example, there were some more complicated ones in the Graham-Denning model. We could build those out of combinations of these primitive operations. These primitive operations are the basic building blocks, and we could build all the operations of the Graham-Denning model out of them. Okay? If I can check some conditions, I check those preconditions in the table, and then I do the primitive operations that have the effect that I want, then I'm good. What's a command? So a command in the HRU model looks like a row out of that table from Graham-Denning. The table said, okay, there's a precondition, right? That's this if section up here. And then there's a transformation made to the access control matrix. That's where this sequence of operations down here occurs. So I check to see if some condition is true, and if it is, then I perform some operations. Pretty simple basic idea, but it allows me to create some fairly sophisticated commands that can do some fairly complex tasks. It basically allows me to build all of the Graham-Denning stuff and more. As an example of that, here's a really simple one. This is a mono-operational command. It's a term that comes up in the paper because it only has one primitive operation in it. So the command is, I want to confer the read right from me, the owner, to you, my friend, on a given file. So if the access control matrix for my row and that file contains the token owner, that means I'm the owner of the file. And then I am allowed to read into your entry in the access control matrix for your row and the file column. All right. And I can have a confer write, confer execute, confer print, confer delete, whatever. You can imagine doing all these different things. Now, here we go. In the HRU model, a protection system consists of two things: a finite set of writes and a finite set of commands. So I can have any commands I want. I can have any writes that I want, right? The writes don't have any semantics in this system. They're just tokens, right? They may have meaning to me, like read or write, but within the HRU system, they're just tokens. They're just undigested tokens. But I can have any commands that I want, and I can build those commands out of those 6 primitive operations. A configuration is basically the instantaneous state of the protection system. So at any given time, I have the access control matrix, and I have the rows, which are the subjects, and the columns, which are the subjects and the objects. So I could think of the configuration as being a triple. It's the set of subjects at that moment, the set of objects at that moment, and the access control matrix at that moment, right? Conceptually, that's the configuration. And great, whenever I perform an operation or I perform a command, I then change that. I might delete a subject or add an object or add a write or delete a write in the matrix. And so I evolve to a new configuration. And I can sort of draw that out over here, right? So here I have a sequence of commands, C1, C2, C3, and that leads to an evolution of the configuration of the system. So I evolve from my initial configuration over here at Q1 all the way over here to the final configuration at Qn. Now, I am curious about Q1 and Qn. I would like to know if given a safe state, a state where I have rights allocated in a way that I believe is safe, can I evolve to an unsafe state, a state in which somebody maybe has too many rights over objects I own and the system has gotten out of my control? So I now have turned this safety problem, this security problem, into a reachability problem. And that's good because oftentimes I can solve those. Okay, so we're going to talk about the existence of a sequence of commands leading from an initial configuration to some final configuration, and we'll write that like this, right? Q derives, after 0 more steps, some Q prime. Now, we start to formalize some of the notions that we'll need later. Given a protection system and the command C, we say that command leaks the write R from a given configuration if, when I run that command on that configuration, it puts the write R into a cell of A that did not previously contain it. It's a lot of words, but what it means is I run a command and a write is granted where it didn't previously exist. In that case, it says I've leaked the write. Well, I can leak writes all the time, right? One of the things that I can do, one of the primitive operations, is to add a write to a cell. So anytime that operation happens, oh great, I've leaked a write. We'll come back and deal with that issue in a moment, because we don't really want to say that every operation like that is leaky. We only want certain ones to be leaky. And we'll come back and address that problem in just a moment. Over on the right, we say, given a protection system and a generic write R, we say the initial configuration Q0 is unsafe for R if there's a configuration Q and a command C such that the following two statements are true. So I can go from Q0 to Q, right? I can evolve the state of the system from Q0 to Q, and at that point, the command C will leak the right R. So the command C at this point, operating in state Q, or in configuration Q, will result in the right R being placed in the table where it wasn't previously. Otherwise, we say Q0 is safe for R. All right. I hope you got all that. Now, let's go back and deal with the issue we noted a moment ago. A subject can intentionally grant a right to someone else. I can say, you know what? You have the right to read one of my files. And I don't think I should consider that to be a leak. That's probably an intentional thing that I'm doing. I understand what I'm doing, and that seems fine. So when we're talking about leaks, before we do the analysis, we delete certain parts of the access control matrix. Namely, we delete the file owner, and we delete any, we'll call them reliable parties, that could also grant that right on the file. So reliable parties might be the overall super user of the system. So now that I've deleted those, think of this for a minute. I've got a particular file, and I'm worried that a right, like reading that file, could be leaked. So we remove me from the model. Since we've removed me, I can't grant that right. I'm the file owner, but I'm not in it anymore, so our analysis doesn't include cases of me granting that right. But if the system evolves in such a way, with other people doing commands and so forth, it may evolve in such a way that that right ends up in somebody else's entry for that file, meaning somebody else has managed to obtain the read right to a file that I own without me being aware of it or doing anything to cause it. And that's what we ultimately mean by unsafe and by leaking. So they deal with two theorems in this paper. Theorem 1 says, there is an algorithm which decides whether or not a given mono-operational protection system, remember I mentioned that before, that's where the commands all just do one operation. Mono-operational protection system and the initial configuration is unsafe for a given generic right R. So they can do that. It's decidable. It's not necessarily practically decidable, but it is decidable. So I'm just doing single operations. So they point out, hey, I can ignore certain operations. I can ignore deleting stuff, right? Because deleting stuff is not going to add a right to the matrix. So I ignore deletions. I just consider the others. And once I've done that, the system can only evolve in certain ways, right? The system can only evolve in a very specific set of ways. Over time, I'm adding rights to cells. Eventually, those cells are full. I don't have any other rights I can add to them, right? There's a finite, R is a finite set. Eventually, I've given all the rights to everybody. So if I'm looking at that, there's a maximum length sequence that I have to consider. Since all the sequences that I have to consider for that have a bounded maximum length, it follows that there's a finite number of them. Those sequences are made up of commands. There's a finite number of commands. The sequences have finite length. So therefore, there's a finite number of them. It might be a gargantuan, humongous number, but it's still a finite number, which means that theoretically, at least, I can look at them all and check them all, which means that it's decidable. maybe it takes the rest of the life of the universe to do it, but it still makes it decidable. And since I know that it's decidable in that case, maybe there's actually a much faster way to do it, a much better way to do it. I don't know. But for the sake of the theorem, I just had to find one way to do it. Theorem 2 is a little more interesting, maybe. Theorem 2 says it is undecidable whether a given configuration of a given protection system is safe for a given generic right. Wow. This says, you know what? You start adding just ordinary, whatever commands you want to your system and give it up. We can't decide. Now, there are some models that come after this that do their best to recover the ability to analyze it, but this theorem is strong and it persists. How do they prove this theorem? Well, it turns out the little model we're talking about, the tiny little model with the 6 primitive operations and the access control matrix and the finite number of rights, that is sufficient for us to encode a Turing machine. And so they turn it into the halting problem. So here's how that works. I encounter a Turing machine. I'm walking down the street, minding my own business, and I trip over a Turing machine. And I say, wow, that Turing machine was in my way. I wonder if it halts. So there is a way, given in the paper, for me to encode that Turing machine, any old Turing machine, into the HRU model, into a protection system. So that Turing machine can be encoded as a protection system, such that granting a right, putting the little R in the cell in that table, corresponds to terminating the Turing machine. So if I can solve that, right, if I can decide whether a given configuration of a protection system is safe for a generic right, I can in turn show that the Turing machine I encoded halts. Wow. I already know that I can't prove halting there, so something must have gone wrong. So maybe I can't encode any old Turing machine into a protection system, but I can, and they explain how to do it. You might object and say, well, Turing machines have unbounded tape. Well, so does the protection system. I can just keep adding objects all day long, which creates new cells in the matrix. All right. So what else could go wrong? The only other thing that could go wrong is my ability to prove safety. So that's what I can't do. I can't prove safety. Otherwise, I could use protection systems to solve the halting problem. So there you go. Now, it turns out the proof in the paper contains an error. And the error was later corrected. And if you want to see the correction, there's a tech report that you can find here that contains that. But it turns out that didn't change the result. They just patched a little hole in the proof. It's still the case that we were NP complete and it's undecidable. It's the way the life is. All right. Something that sort of comes out of all of these models is a basic principle of security. And that is maximize trustworthy things like the math of the system and the things you can prove, and minimize the things that you just flat out trust, right? I trust Brenda. Why? Just because, with a name like Brenda, she couldn't do anything wrong. That's just trusting something. In this case, trusting another subject or another person. Or I could maximize the trustworthy things, the things where I have some ability to prove that they are trusted. And that's sort of the lesson of a lot of these systems that we've seen so far. That's why so many of them fall back on trying to build a mathematical model around security. But it's hard. At the end of the day, somebody's going to be a super user, right? All these systems, all the systems we talked about, All the models we talked about, every last one of them, at some point, somebody's got to be there to grant the initial permissions. Somebody's got to be there to get the ball rolling. You got to have someone that kicks the whole thing off. So, try to minimize the things that you just trust just because, and try to maximize the things that you trust because you know something about them and you believe reasonably, again, for reasons that you can trust them. There's homework. It's due in a week. And the homework is to do some stuff with the Graham-Denning rules. So go back to that table. Put yourself in the system. Your name is root. So now you're in the system. You're the only user. And execute that script you see over on the right. So create a subject, create another subject, create an object, start granting permissions. You might see a little asterisk there. That means you're granting a permission that is transferable. And just walk down that little script, and you'll, at the end of this, produce an access control matrix. And that is what I want. I want you to give me that access control matrix that's produced by executing those commands, those protection rights, if you will. A safety principle is that only the owner can grant rights to an object. Now take a look at your matrix, and does the sequence of events that you just did, does it violate that principle? So I want you to apply the Graham-Denning stuff, and then I want you to try to apply the safety principle to what you've got out at the end. All right. That's it.